Okay, so exam 2 is over chapters 6 through 12. 6 through 12, box plots all the way to the last part of probability. And we learned about something called the multiplication rule. And chapter 12, you guys can see, is called the addition rule. So this is the last case of probability that we're going to do. And it kind of ties in everything we've been doing so far. It says, hey, remember, the chance or the probability of an outcome is just the number of that outcome over the total number of possibilities. Something that seems straightforward, but if you're ever confused, think back to that. It should help. Number of successes over the total number of possibilities. So sometimes with probability questions, it can be helpful to list out all the ways that a chance process can turn out. And we call this the sample space. Right? That was our first probability definition, was sample space. So we can list out the sample space for really any event. Some might be more complicated than others, but like this, it says 2 dice are rolled. What's the chance of getting a total of 4 spots? What's the chance of getting a total of 7 spots? Well, basically I could list, there's 36 possibilities when you roll 2 dice, right? Because there's 6 sides on each die. There we go. 36 possibilities. So here's die number 1. Here's die number 2. And then here are all the 36 possible combinations of numbers that I could get when I roll 2 dice. So if I have this picture, and you can always make this picture, right? You could say you could get a 1 and a 1, you could get a 2 and a 2, you could get a 1 and a 2, etc. We could list all the whole sample space. But if I have this picture answering this question, it says, what's the probability of rolling 2 dice and getting a sum of 4? So what's the chance of getting a sum of 4? So this, without the picture, I could say, well, what does this mean? A sum of 4? I guess like I could get 2 2s. That would add up to 4. I could get a 3 and a 1. I could get a 1 and a 3. I think that's pretty much it. Or what I could do is go ahead and look at my sample space and say, here are all the ways I can get a sum of 4. And there's only 3 of them out of 36 total. So I could do that. That would work. I could do this with any of them. What's the probability of getting a sum of 7 for the next one? Let's see. What's the probability of getting a sum of 7? Well, anytime you roll 2 dice, there's 36 possibilities. And the chance of getting a sum of 7, let's see. I'm going to highlight all of them. Sum of 7. So that would be this. Ooh, yeah, it's like a nice diagonal. How many is that? 6? Yeah, 6. So the chance is just 6 out of 36. Or I could list them. Even if I don't have the table, I could think about all the possible combinations. Last one. Let's see. Probability of getting a sum of 8. I'll just go ahead and list these out. I can get a 4 and a 4, a 5 and a 3, 3 and a 5. I'm forgetting some. 2 and 6, 6 and 2. I don't want to add 1 and 7 because the die doesn't have a 7. So these are my only ones. This is 5, right? 5 possibilities out of 36. So anytime you're rolling 2 dice, you can think about the sample space and know there's 36 total possibilities, and then just count how many of them are successes. So that's, we've seen stuff like that before. But the addition rule, so the reason I introduced this sample space idea is because the addition rule, it's really helpful to think about the sample space. So let's look at the addition rule. All right, it says back in chapter 11, we learned the multiplication rule. Hopefully you guys remember this, right? The probability of A and B is equal to the probability of A times the probability of B. So if we have an and situation, we're going to multiply. So probability of A and B, just multiply them together, right? We did that earlier in class today. That was the multiplication rule. That was chapter 11. Chapter 12 is all about the addition rule. So the addition rule is actually for situations that involve or. And we can see the probability of A or B is equal to, it's kind of similar, the probability of A plus the probability of B. So with or, we're going to add. But then there's this minus the probability of both, of A and B. And actually, in terms of probability questions, there have been studies done that give students, like intro stats students, probability questions. And this idea of or, a lot of people remember, okay, I need to add the two together, but they forget to subtract the probability of both. So we're going to look at why we have to do that. So first of all, our latest definition, let's see, our next definition is mutually exclusive. So here's my addition rule. And I need to think about, are the events mutually exclusive? So mutually exclusive means the two events cannot happen at the same time. So they cannot happen at the same time. It's impossible. So if the two events are mutually exclusive, then hi. Okay. If the two events are mutually exclusive, then they cannot happen at the same time. So that's subtracting the probability of A and B. If they can't happen at the same time, the probability of them both would be 0. So the nice thing is, if they're mutually exclusive, we can just add the two probabilities together. I can literally just take probability of A plus the probability of B. So this is if the two events can't happen at the same time. So this is nice. We don't have to remember that second part, subtracting the probability of both. Another word that means exactly the same thing is disjoint. So disjoint and mutually exclusive are synonyms. They basically mean that the probability of both is 0. Okay, so we'll do some examples so you guys can see how to do this. It says the following two situations illustrate the difference between mutually exclusive, two events that cannot happen at the same time, and non-mutually exclusive, two events that can happen at the same time. So the first one, it says pick a random person enrolled in Stat 100. What's the probability, what's the chance that the person is either in online or in person? Okay, let's see. Maybe we can try this. Raise your hand if you're in Stat 100 online. Do I have any online people here? Sometimes they come. No, there's no one. Oh, there's one. Oh, hi. Hi, other online people. They're on video. They're seeing me, not you guys. What about if you're in person? Raise your hand if you're in person. Are all of you guys in person? Yeah. Okay, cool. No one raised their hand twice. Like, you didn't raise your hand twice, right? You're just in online. Yeah. Yeah, okay, good. So these, you can't be in both, right? So these would be mutually exclusive events because they cannot happen at the same time. So that's all that means. They can't happen at the same time. Our second example says pick a random person enrolled in Stat 100. What's the chance the person is either wearing jeans or female? So we can do the same thing. Go ahead, raise your hand if you're wearing jeans. Jeans, a lot of people. Okay, put them down. And then raise your hand if you're female. Did anyone raise their hand twice? I totally did. Yeah, some people did. So if I just added all the people that were wearing jeans plus all the people that were female, I'd be counting people twice. So that's why when we're doing probability, we have to subtract the probability of both. I don't want to count anyone twice. So these events are not mutually exclusive. So here, if I was using the addition rule, I'd have to remember, if I was solving for the probability that you're wearing jeans or female, sure, I could add them together. I could say, what's the probability that you're wearing jeans? Or means to add, plus the probability that you're female, and then minus the probability of both, because I wouldn't want to count those people twice. Okay, so those examples don't have any numbers. I want to do an actual example with some numbers that you guys would see. So on the next page, we can see at the top, this is just, a lot of times people show Venn diagrams when looking at the addition rule. It says, in general, the probability of both is subtracted to avoid double counting. So we saw in the overlapping case, the case where you could be both if you're wearing jeans or female, there's this overlap, right here. There's this overlap of people that are both. But if you're if they're mutually exclusive, like if you're in person or online, you can't be in both, right? I think that's actually impossible. These would be mutually exclusive events because there's no overlap. So there's names for these definitions. The overlap between the two is called the intersection. A lot of times you'll see this written with an upside down U to mean intersection. It basically just means the probability of A and B. And then the union, it says the union of two sets is the set that contains all elements of both sets. So the union is U. So like the union of A and B here, A or B would just be all of A plus all of B. All right. We don't need to spend too much time on that. So I want to do a couple more examples, at least 3 more examples. So example 3 says, what's the chance of getting either a 5 or a 6 on one roll of a die? So the question, it says, are the two events mutually exclusive? So mutually exclusive means they can't happen at the same time. So if you roll one die, the question is, can you get a 5 and a 6 with just one roll? No, right? You'd have to roll twice in order for that to happen. So I'm going to say, are these mutually exclusive? Yes, because they can't happen at the same time. You can't get a 5 and a 6 on one roll. Can't get a 5 and a 6 on one roll. So that's super nice. When I'm doing the addition rule, if they're mutually exclusive, I can just add the two things together. I can just say the probability of getting a 5 or a 6 is the probability of getting a 5 plus the probability of getting a 6. I always like to, just out of habit, say minus the probability of both, but this is 0%. This isn't, it's unnecessary, but just so you don't forget it, I like to write it. So the chance of getting a 5 is just 1/6, plus the chance of getting a 6 is exactly the same. And these have common denominators, so let's go ahead and do 2 out of 6 or 1/3, whatever you want, is our final answer. Okay. Another example of mutually exclusive events, this one says, what's the chance of drawing a card and getting either a heart or a spade? So getting a heart or a spade on one draw. And there's 13 hearts and there's 13 spades. So we'd ask ourselves, are these mutually exclusive? Can you get a heart and a spade on one draw? And there's not, right? No spade, heart thing in the deck. So I'd say this is just the probability of getting a heart plus the probability of getting a spade. And then when I subtract the probability of both, I see the exact same thing, that this is impossible. The probability of both is actually, again, 0. So the chance of getting a heart is 13 out of 52. The chance of getting a spade is 13 out of 52 as well. There's 13 spades. And then that gives me 26 out of 52, or 1/2. And we can see in these examples, the events were mutually exclusive. So we can just add the chances together. But if that's not the case, we do have to remember to subtract the probability of both. So these two were nice. We didn't have to worry about that. But on the next page, there's 2 examples where we do have to worry about that. Okay, so it says, if the 2 events are not mutually exclusive, then here's the thing. You can't just add the chances because you'll be double counting. Instead, you have to add them and subtract the chance that both will happen. So our probability of both isn't going to be 0 for number 5 and number 6. So for number 5, let's see, it says, what's the chance of drawing a card from a full deck and getting either a heart or a queen? Are the 2 events mutually exclusive? So we need to ask ourselves, can you get, if you draw one card, can you get a card that is both a heart and a queen? Yeah, the Queen of Hearts. We can get the Queen of Hearts. So no, because of the Queen of Hearts, because you can get the Queen of Hearts. So we don't want to forget about the Queen of Hearts. We can get it. So I'm going to go ahead and say this is just the probability of getting a heart plus, or means to add, the probability of getting a queen, and then minus the probability of both. Okay, so there's 13 hearts. The chance of getting a heart is 13 out of 52. Plus, there are 4 queens, so the chance of getting a queen is 4 out of 52. But then I counted the Queen of Hearts as a heart and as a queen. So I have to subtract the probability of getting both, getting the Queen of Hearts. And there's only one of those in the deck, so I'm going to subtract the probability of getting both. And then these all have common denominators, so I'm just going to go ahead and simplify. 13 plus 4 is 17, minus 1 is 16 out of 52. And in our last couple of minutes, one last example. It says, what's the chance of rolling a die twice and getting either a 5 on the first roll or a 6 on the second roll? So we're going to go ahead and do this. What's the probability of getting a 5 on the first roll? Oops. Or, there's more than that, or getting a 6 on the second roll. So I would say this is just the probability of getting a 5 on the first roll plus the probability of getting a 6 on the second roll, and then minus the probability of both. So if we think about this, if we're rolling a die twice, we're rolling the die twice. So the question is, can you get a 5 on the first roll and a 6 on the second roll? Yeah, that seems legitimate. We could definitely do that. So I have to make sure when I do this, the chance of getting a 5 is 1/6. Right? The chance of getting a 6 is 1/6, but I have to subtract the probability of both, the chance of getting a 5 and a 6, since I am rolling twice. So I'm kind of running out of room here, but let's go back up at the top. Just what does this mean? So I'd have to subtract the probability of both. So the probability of both is just both events occurring. That's the probability of getting a 5 on the first roll and a 6 on the second roll. Okay, so, and then this is just the multiplication rule, right? The chance of getting a 5 on the first roll is 1/6, and means to multiply. And then the chance of getting a 6 on the second roll, we've done questions like this, right? 6 on the second roll is exactly the same. So this gives me 1 out of 36 if I simplify it. So I have to remember to subtract that, to subtract this 1 out of 36, or my answer isn't going to be correct. And if I look at the original sample space, like if I look at the very first page of chapter 12, what's the probability of getting a 5 on the first roll? Here is where the 1/6 comes from. There's 6 out of 36 ways for that to happen. Or getting a 6 on the second roll, I don't want to double count this one that shows up twice, which is getting both of them. So I only want to count that once. So I'm just going to write down the final answer to this. If I simplify it, if I make common denominators, this should be 11 out of 36. Okay, these are the last two. It says, what's the chance of getting at least 1 5 on 6 rolls of a die? So right away, I see this key word, at least 1. And on the exam, there's a student in my office this morning, and he was like, I'm confused at when do I use the 1 minus? When do I have to use the complement instead of just solving something directly? It's as simple as if the problem says these words. Like if you see in the problem the words at least 1 or not all, then you can cross out all the answers that don't have a 1 minus, because those are the 2 cases where it's easier to look at the complement. So here I know my answer is going to have a 1 minus because it says at least 1. And we learned before that the rule is the probability of getting at least 1 5 on 6 rolls. So if I think about what that means, it's confusing, right? At least 1 5, that means I could get 1 5, or 2 5s, or 3 5s, or 4 5s, or 5 5s, or all 6 5s. So I don't want to do all that. That would be a bunch of different probabilities. The only thing that's not included in at least 1 is getting no 5s. So at least 1 and none are complements. So 1 minus the probability of none, in this case, means no 5s. So I'm actually using, down here, I'm using this rule. The probability of at least 1 is equal to 1 minus the probability of none. And if you're still confused on how, like, where this rule came from, I made a video about it, like a short, I think it's like a 5-minute video that I will send to you guys in case anyone's still confused about that. But even if you're a little confused by that, how would you solve this problem? These 2 things are equal. So instead of focusing on this complicated at least 1, I'm going to focus on this, the complement, getting no 5s. If I do 1 minus that, I'll get my answer. So the chance of getting no 5s, that just means, okay, I can get anything but a 5. So not getting a 5, the probability is just 5 out of 6, right? On the first roll. And on the second roll and on the third roll, the probability doesn't actually change. So I would just say we're rolling 6 times. So my answer is 1 minus 5 over 6 raised to the 6th. Yes?
Are there points where we wouldn't use exponents? Are we always going to have exponents?
So the question is, are we always going to have exponents in our answer? And that depends on if you're doing something like, so for rolling a die, if you're just rolling it once, then no, you won't have any exponents. But the exponent, what this means is, so it means 5 out of 6 times 5 out of 6, 6 times. And so it's saying we get a non-5 and not a 5 and not a 5 and not a 5.
It doesn't tell us that we're rolling more than once.
Yes, exactly. Any other questions? All right, let's do this one. And I guess just to, for the last, I'll say this one more time, I guess, in class. I feel like I've said this a bunch, though, so sorry if I'm repeating myself. But the reason we use this rule is because at least 1 5, again, what it means is we could get 1 5, or we could get 2 5s. That would be at least 1 5, 2 out of 6, right? Or 3 5s. or 4 5s. This is crazy. There's a lot of them. Or 5 5s, 5 out of 6 5s, or all 6 5s. So I think everyone agrees with me that we don't want to do this. There's multiple ways to get 2 5s. Like we could get a 5, then not a 5, then a 5, then not a 5. It gets crazy. The only thing that's not included in at least one is getting 0 5s. So that's why we can use this rule. All right. Good. And the same thing is another complicated scenario is this, not all. So if I was reading this problem, what's the chance of rolling a die 3 times and not getting all 2s right away? I see the not all, so I know my answer is going to have a 1 minus in it. The probability of not getting all 2s, again, this, just even thinking about what this means is complicated. That means we could get 0 2s, right? 0 out of, we're rolling 3 times. So 0 2s, that would be not all 2s. I could get 1 2. I could get 2 2s. The only thing that doesn't include the not all is getting all 2s. I couldn't say that 3 2s, if I roll 3 times, is not all 2s. So instead of finding 3 different probabilities, I'm just going to do 1 minus the probability of getting all 2s. And then again, these two are equal, so focus on the side that's not super complicated. The chance of getting all 2s, we've done this a bunch, right? The chance of getting a 2 on the first roll is just 1/6, and then we're rolling 3 times. So that's why I'm going to use the exponent, because I want to get a 2 and a 2 and a 2. Question? Actually, no. So she said, is the way I got the exponent, because 0 2s, 1 2, and 2 2s, that's 3. No, the exponent comes from we're rolling 3 times. So that was actually just a coincidence there. Or does that always work? Does that always work? Let's see. 1, 2, 3, 4, 5, 6. Actually, that I feel like that will always work, because you'll always have 1 less. Yeah. Yeah, that definitely works too. Okay, that's another way to think about it for sure. I always think about it by how many times you're doing the thing. So like if you're drawing 3 cards, you're going to raise, and it's with replacement, you're going to raise it to the 3rd power. If you're rolling 6 times, you're going to raise it to the 6th power.